Okay, let's start part two of our introduction to casting and molding. We left off part one talking about how we get the liquid metal into the mold, and remember that there's basically two ways we can fill the mold fast, or we can fill the mold slowly, and both of them have trade-offs, right? Filling the mold fast is going to allow the liquid metal to get into all the nooks and crannies, and the metal is not going to solidify prematurely. The downside to that, filling it fast, is that we're going to get higher rates of oxidation because there's going to be more splashing. On the other side, filling it slowly is going to allow for better material properties, but it's also going to possibly create a situation where we have metal prematurely solidifying. It's also going to extend the cycle time. So that's, a less efficient way to cast. Okay. So moving on to this, we're looking now at how the metal is going to solidify. Okay. Now in this example here, we're looking at a graph. The vertical axis is temperature, right? And the horizontal axis is time. Okay. And in this example, we're looking at a pure metal, right? So there's no alloying element. So this is just a look at a kind of a perfect curve, right? Adding in alloying elements is going to mess this up, and we're going to look at that next. But let's just try to understand what's happening here. So this point right here, where my cursor is, this is where we start the process of filling the mold. Okay, the mold is actually, you can imagine that this temperature right here is going to be above the melting temperature, so it's a very high temperature where the metal is all liquid. All right, and then at this point right here, you can imagine, let's say that this point exactly corresponds to where we start to fill the mold. Right? Now, as soon as we take our liquid metal from our vessel, our crucible, right, and we start to pour it into the mold, as soon as we start to pour it into the mold, it's going to start to cool, right? It's going to be hit with the outside air temperature, maybe the temperature of the mold, whatever. It's going to start to cool right away. Okay, so this is that cooling process. So we can see as the metal is being poured, right? So this is time. So here we're pouring the metal, and as we're pouring the metal is starting to cool, right? The metal is still liquid, but it's liquid cooling, right? So the liquid is cooling, it's cooling, it's cooling. And then we get to this point right here, right? And we don't know how much is already in the mold, right? But whatever it is, at this point right here, the metal, some of the metal, we can think of the metal in the front, right? The first liquid that was poured in, that metal that's in front of the mold right there, not the metal that's still in the back being poured. But that metal right there is going to start to solidify, right? It's called freezing in this graph, but basically that's the solidification process. What point is that? Well, that is corresponding to the melting temperature, right? Any temperature of the liquid metal below the melting temperature means that it's going to start to freeze. It's going to start to solidify. And so once that happens, it's going to continue to solidify through time, right? So here, this is just all the liquid starting to solidify. So you can imagine right at this point right here, just a little bit of it is solidifying. And as time goes on, more and more and more and more and more solidifies until we get to this point where everything is solid. Okay? So that's called the total solidification time. From the time that we start filling the mold all the way to the time when everything is a solid, that's called the total solidification time. All right? So the freezing or solidification is completed at this point. So what happens down here? Well, this is just the part being cooled. You can imagine that even after it's solidified, even after you pour the metal into the mold, and there's nothing liquid, it's all solid, you're not going to be able to go and grab it with your hand. It's still going to burn you. It's still going to be white hot. So this is just further cooling down to room temperature. Okay. Now, that's an idealized example, because we're talking about a pure metal. We don't cast pure metals, we cast alloys. So how does an alloy affect this area right here? And basically what it does is it changes that horizontal line, this line right here from where freezing begins and freezing is completed, or the solidification, local solidification time. It turns it into a sloping line, right? And what's happening here, because we have an alloy, and an alloy is basically two molecules together, two objects, iron and carbon together. We're going to get let's say the iron solidifying before the carbon, or the carbon before the iron, right? And so that's what's happening here. Different parts of it are solidifying faster than other parts. And that's why we get in here what they call solidus and liquidus. Basically, this area right here is where we have some chunks of solid in the liquid. All right. So it's not as uniform as this, where with a pure metal, it's just going to all start to solidify. Here, we have chunks solidifying in the liquid. And that's what this over here shows. This is showing in this area right here, we're talking about this point right here down to this point, right? This is temperature, so the temperature is going down from here. And what's happening is this is all liquid solution, right? This is all liquid. And it gets to right here, and what happens? Some of it turns solid, and we have solid and liquid together. And then boom, at this point right here, everything turns solid. So that's what's happening there. Okay. So the solidification process, and this is very important, maybe more important than the filling the mold part of it. But after the mold filling, the molten metal has to solidify, right? That's the whole point of casting. We're going to fill the mold with liquid metal, and then we're going to allow it to cool. To solidify it, it's going to cool. It must cool down. Non-eutectic alloys have a freezing range. Non-eutectic alloys, okay? That is, alloys without that perfect little dip right down in the eutectic diagram. Shrinking occurs during solidification. All right, now this is important. Shrinking is going to occur. Why? Well, because we have clumps that are cooling and solidifying, and that's going to cause the liquid volume to shrink, to decrease. And this is from a crystalline ordering of the atoms. That is, the atoms start to organize themselves. And then after solidification, there's going to be a contraction. So there's actually two stages of a decreasing in volume in a casting process. First, we have shrinkage, right? And then we have contraction. So think of it, two stages of this. I don't want to say shrinking. Two stages of this volume contraction. We have shrinkage, which is a large volume contraction, and then we have contraction, which is a smaller volume restriction. Okay, liquid to solid is a phase transition, right? Obviously, from liquid to solid, we're talking about going through a different phase. Remember that there's 4 phases. We have liquid, solid, and gas, and then we have plasma, right? Plasma is the often forgotten one of those, but there's 4 phases of a material: liquid, solid, gas, and plasma. So the solidification process. The solidification process is from the liquid temperature to the solid temperature, right? So looking over here, T liquidus to T solidus. If we go back here, T liquidus is right here. T solidus is right there. See that right there? That's T liquidus, and that's T solidus. All right. T liquidus is the temperature above which everything is liquid. T solidus is the temperature below which everything is solid. All right. So this is called the solidification range, and it is this period right in here. It's this area right here. And this is referred to as shrinkage. It's compensated by overfilling the mold, right? So how do we compensate that? Right? We want parts that are going to be accurate in size and shape. So what happens is we overfill the mold. We fill it so that there's a little bit of extra reservoir, and we can see that right here. This area right here, this is where we overfill the mold. So as it shrinks, it draws this down, right? So it continues to feed the mold while it's shrinking. And this is governed by the specific heat of the material. And then we have contraction, and contraction is from T solidus to room temperature. So it's from this point down to this point right here. Or we could go back here. It's from this point right here down to this point, right? This is where the contraction occurs. And contraction is compensated by oversizing the mold, right? So if we want to cast something that is 1 inch by 1 inch by 1 inch, we might make our mold 1.1 inch by 1.1 inch by 1.1 inch. Noting that as it contracts, it's going to go from that filled 1.1 cube down to it's going to contract down to a 1 inch cube. And this is governed by the coefficient of thermal expansion. So we can predict this. It's not perfect, but we can get very, very close to predicting that. And so we can create objects that the end result is, after we're done casting them, they have relatively good geometry. It's not perfect, right? It's not like machining, but we have relatively good geometry. All right, and so continuing on the solidification process, it's going to help us in the solidification process to locate runners and risers on the thicker sections, right? Runners and risers. Remember, risers are areas where we can have overfilled liquid that is going to be drawn down when the solidification occurs, okay? We have inflow from the runners and gates, right? This is a gate. And we have outflow, right? As the solidification happens, there's going to be gases that are escaping. And so these can come out of the risers and the feeders, right? All right. So let's talk about some terminology for casting. What we're looking at here is a sand casting example, but some of the terminology is going to be the same no matter the casting type process that you're looking at. The main thing I want you to get here is that the drag is the bottom part of the mold and the cope is the top part of the mold. How can you remember that? Well, remember drag D for down, right? Drag D down. So the drag always goes on the bottom or down. The cope is on the top. And then we can, if we want to cast a hollow shape, we use what's called a core. And a core is just an object that fills in the hollow shape, and the liquid flows around it, and then we create a hollow, right? You can see that right in here. All right, so what are some casting defects that we run into? Well, there's 3 main casting defects. We have porosity formation, internal stresses, and distortion. All right, porosity formation are these little bubbles or holes that we see in the casting. All right, and they're from bubbles of gas that aren't escaped. All right, internal stresses are when we have tension that builds up in the casting, and it's got to find its way out, right? And we'll look at, there's some videos that I want you to look at in the Canvas module that will show you what happens when you have these internal stresses, basically exploding parts, which is not good. And then we have distortion. Distortion is when through contraction and to some extent shrinkage, the shape of the part is going to become distorted. It's going to change, and we can get fractures in the part because of that if we don't plan our casting process properly. So porosities. Shrinkage porosities are means that the shrinkage is not fully compensated by the extra inflow material, right? So we didn't have enough material to begin with, so it started to shrink, but there wasn't an additional material to fill that void, and so we have problems there. How do we remedy this? Careful feeder design, right? The other type of porosity is, like I said, trapped gas bubbles. These are difficult to eliminate. Microporosities or dispersed gases, they're better than macroporosities, large bubbles, right? Microporosities, which are basically small little gas bubbles, are better than large gas bubbles. Maybe this is an obvious thing, but small gas bubbles better than large gas bubbles. No gas bubbles is best, obviously, because all these gas bubbles are going to be signs of weak or points of weakness, right? You don't want the landing gear on your airplane to have these porosities in it. Internal stresses arise from the cooling rate and how thick sections and thin sections cool differently, right? So thin sections are going to cool faster than thick sections, right? I think that's obvious, right? Thick sections are going to have more heat in them, so they're going to stay liquid longer. Thin sections are going to dissipate that heat, and they're going to solidify faster. So different cooling rates between thin sections and thick sections are going to cause temperature gradients. We can see in these examples, like let's look at this rim, right? So this is a cutaway section view of a wheel, a rim for a car. And you can see the bright yellow are areas that are still very hot and are still going to be liquid. The purple areas and even the blue areas are areas that are solid, right? They've already cooled enough so that they're not going to be liquid anymore. And you can see this area right here, these areas right there are going to be areas where we might expect to have internal stresses, things that we have to deal with, okay? So the temperature gradients cause the differences in contraction, right? Contraction differences cause stress, right? When you have two areas that are contracting, but at different rates, they're going to pull against each other. And that pulling is going to cause stress, or is stress, right? That's a force, and so that's a stress. When this stress is greater than the material's yield strength, right? Deformation, if the casting is unconstrained, that is, it's just sitting there on the ground, it's going to deform, right? If it's constrained, so if it's held in the mold, it's going to cause internal stress. That is, the material is going to solidify around that stress, and that stress is going to be locked in. And so what happens is whenever we then bend the metal or even cut the metal, that internal stress is going to be released like a bomb, and it's going to explode. And there's a video that I want you to watch in the Canvas that I've dropped into the Canvas module for this, where it actually shows the part exploding. All right, and that's definitely not good. Machining a casting with internal stresses can result in the part warping or, like I said, exploding. So here we're just going to talk briefly about stress strain curves. I'm not going to talk too much about this. I just want you to be aware of stress strain curves. It's important. You should also know the different parts of the stress strain curve. Okay. So, the different parts here, this area where we have a straight line going at an angle, this is the elastic area. This is where we have elastic deformation. What is elastic deformation? Well, think of bending a metal, but you don't bend it so much, and so when you release it, it goes back to its original shape. That's an elastic deformation, right? Once you go past that point, so if you take a piece of metal and you bend it slightly and release it, it's going to go back. But if you take that same piece of metal and bend it more, at some point you're going to release it and it's not going to bend back. And that's this area right here. And that's called plastic deformation. So we have elastic deformation, where you bend it and release it and it comes back to its original shape. And then you have plastic deformation, where you bend it so far and you release it, it doesn't go back to its original shape. Some other important areas, we have the yield strength, which is right at the division between elastic and plastic deformation right there. That's the yield strength. Fracture strength is at the very end. We have the ultimate tensile strength, which is right at the top of this curve, right? Once you get above this curve right here, what happens is you have fracturing, right? So we don't want to go past this curve, right? In fact, we kind of don't even want to get up here. But up here is better than here. So different materials are going to have different stress strain curves, right? Material A is strong and stiff, right? But it fractures at a low, it's not very ductile. It fractures, and does not, bend very much. Let's put it that way. B is the most brittle because it fractures suddenly. So B, think of B as a piece of glass, right? How much can you bend glass? Not very much. So you're going to be able to bend it slightly and then boom, it's just going to shatter. There's no curve where it comes around. All right. C is the most ductile because it extends the stretch the most. So C, think of C as like aluminum, right? Aluminum is very bendy. So we can bend aluminum very much and it doesn't really fracture until we really, really bend it a lot. And D breaks. D basically bends and then it just fractures. All right. So here's an example of a stress strain curve for different casting alloys, right? So here's mild steel. There. Strong gray cast iron. Notice, remember we said cast iron is not very ductile? Well, look what happens with cast iron. You bend it and then boom, it fractures, right? That's not very ductile. Aluminum. Look at aluminum. Man, you can bend it and bend it and bend it and bend it, and it really doesn't fracture until it gets way out here. Right? This is pure aluminum. Look at pure aluminum, right? Now, pure aluminum is not going to have that part where it snaps back. Notice the aluminum alloy, because it's an alloy, it has this elastic region. So it has this region right here where it's going to you bend it and it's going to snap back. The pure aluminum has no elastic region. It's just going to start bending. Now, it's still going to bend a lot, like a wet spaghetti noodle, but, it's not going to go back to its original shape. Okay, so these are just some examples. Again, we're not going to cover a lot of the details here. This would be for a material science class. So what is the strongest? It's aluminum alloy, right? Strong means that the stress that it can withstand, which is up here, is like at 550 megapascals, right? That's very high force, pressure, I should say. The stiffest is molybdenum. Where is molybdenum? Right here. So that means that it's going to bend and bend, and notice the elastic region is relatively straight. So it's going to be very, very stiff, very, very hard to bend. But then when we do bend it, it's going to fracture. So a more vertical elastic region means it's stiffer. It's not going to bend, right? As opposed to pure aluminum that's just flippy floppy like a wet spaghetti noodle. Most brittle is gray cast iron. Where is that? Yet right there. It just kind of explodes right there. Here's the weak gray cast iron. Right. And then most ductile is aluminum alloy. Most flexible. Ductile means that you can bend it. All right, so let's return back to casting defects and internal stresses. So here's a computer simulation used to predict internal stresses. And we can see that here we cast it with and without holes, right? So here we can say that this would be a part that has a core in it, so that we're casting it around this. And notice we don't get, we get some liquid areas here. identified by the white and the yellow, right? But not as much as we have here. This would be high. This would tell us that there's going to be high internal stresses. Why? Because we have this liquid region that's going to be solidifying, pulling against all this that's already solidified. So this is going to solidify first, and this is going to solidify last, and it's going to cause internal stresses. So how do we avoid this? How do we avoid some of these casting defects? First of all, choose the right alloys. That's key. Second, we want to avoid drastic changes in section thickness, right? So let's look at the bad ones here. This is a larger section thickness. Notice that this section right here is much narrower than this section right here, right? You can see this in this circle. The diameter across here is smaller than this. So this is going to solidify after this area solidifies. Again, same thing here, right? This area is going to solidify, still going to be liquid while this is turning into a solid. And use flowing organic shapes without sharp radii. That's why we have all those fillets and rounds on cast parts, because it makes the liquid flow much better, all right? These corners are bad, right? It's tough to even get the metal into that so that it can start to solidify. All right, so a couple slides we're going to finish up with on casting microstructure and properties. Okay, so metals actually have a crystalline grain structure. If we cut a metal open and look at it under a microscope, we're going to see grains. Okay, and we want to control that grain growth. Pure metal is shown right here, right? And so in a pure metal, we're going to get all this nice grain structure. Notice how geometric it is, right? Keep in mind that this is as a liquid turns into a solid, right? And so a pure metal is just going to be constrained by its own geometry. And we get this nice shape. We have the chill zone here, which is going to solidify first. Then this solidifies, and this is the last area to solidify, right? Because it's cooling from the outside in. The B is the metal alloy. Now notice in the metal alloy here, we kind of have some what looks like pure metal, but then we have this inner area here, which is called the equiax zone, and this is where we start to have some of our alloying agents in there, okay? And then finally, we have the metal alloy with nucleating agents. These are agents that we add in there, such as the magnesium with the ductile iron, that are going to help it to make a completely equiax structure here. Okay, so this is kind of what we're used to seeing. As the grain size goes down, strength is going to go up, and toughness is up. So this is not going to, remember how a pure metal, remember back here, how does a pure metals don't do very good. They're like wet noodles, right? So as the grain size goes down, strength and toughness go up. So this is going to be tougher than this. As the grain size goes down, alloying elements are distributed more homogeneously. Here, the alloying elements are not distributed homogeneously. They're just kind of in zones. And here, wow, everything is all mixed up. Homogeneous means mixed up. It's mixed up better. Okay? So fine equiax grain structure is the best. So what we want is this grain structure, but we want a fine grain structure. Okay? Segregation is the non-uniform distribution of dissolved elements that result from solidification. We don't want that. Imagine that we had all these darker, think of those as alloying elements. The alloying elements help to give the strength and toughness to the metal, right? Think about if we didn't control that and all these alloying elements were down in the bottom or in one corner. Then we're going to have some weird weak part of the metal and a stronger corner. So we want we don't want the grains, the dissolved elements to be segregated. We want them to be spread uniformly throughout. All right, so there's different. So here, this begs the question. So what are these alloy and nucleating agents, and how do we combine them, right? So it's kind of like cooking, right? You know when you need to add more salt, more pepper, maybe a little bit of paprika, maybe some thyme and oregano. That's what these alloying elements do. So there's 4 categories, 4 different types of alloying elements. We have elements to improve processability. That is, being able to make the casting faster and better. We have elements to improve the material properties, to make it stronger or more ductile. We have impurities that reduce the properties. These are things that we don't want in, but invariably they get in, like oxidation. All right? And then we have minor additions to offset impurities. Okay? So we have bad things that get in that we can't avoid getting in, but then we have things that we can add to help mitigate the impurities, right? And so here's a table that I put together. So, common aluminum is a common alloying element for cast steel. So is boron, chromium, right? How do you make chrome? Well, you add chromium as an alloying element, right? Copper is also used with cast steel. Manganese, silicone. Well, look at that. Silicone is used in all of them. Cast iron, cast aluminum, and cast steel. So is manganese. Now, I don't go into which ones do the different things. That's kind of beyond the scope of this class. Your book touches on it a little bit, but it's really beyond the scope of what each one does. That's more for material science and manufacturing technicians. So then, finishing up with cast structures, microstructure, and properties. Determinants, what helps to determine the grain size and shape? Remember that we want a smaller grain size, okay? That's going to be affected by the cooling rate, how quickly or slowly it cools, what type of mold we use. Now, when we're talking about mold, we're talking about maybe an insulated mold, like a sand mold, versus a mold that's going to be chilled from the outside, or a metal mold, right? For metal casting. The size and shape of the casting. Large castings are going to solidify slower, and so therefore they're going to have a certain grain structure than small castings, which are going to solidify faster. And then what alloying elements we put in there. So for a given casting alloy, as the casting size increases, casting properties decrease. So you want to keep your castings as small as possible. Sand casting is not the same as metal die casting. So if you sand cast a part and then you metal cast it, you die cast it, same part, same geometry, they're not going to be the same parts. They will have different material properties. And so the casting processes are different even for the same geometry and the same metal or alloy. All right, so that's it for section 2, chapter 4. Please watch the videos in the Canvas shell, because they help inform you of the things that I was talking about here. And I will see you in chapter 5.